So tonight, our speaker is Alessandro Massarotti. He comes to us from Stonehill College, where he is the Director of Earth and Planetary Science. His academic interests span planetary and stellar astronomy, as well as theoretical cosmology. His research focuses on the observational study of planet ingestion by red giants, the analysis of photometric data to characterize binary systems in open clusters, and the theoretical determination of cosmological vacuum energy. His talk tonight is going to explore the ongoing search for life beyond Earth. So please give a warm Skyscrapers welcome to Dr. Alessandro.
My talk here is supposed to be about finding life. Okay, this is actually good. On my computer, I can see some extra stuff going on there. Finding life away from Earth, right? And it is obviously the topic of a lifetime for me. It's interesting. All of you were interested in astronomy. Of course, I'm interested in this. Excuse me. Could you monitor to look? We can't hear you. Oh, okay. Better? Yeah. Okay. So I say, for all of us who are interested in astronomy or working in astronomy, it's one of the big things is actually to understand if there is any possibility of life out there, especially life that could be intelligent. It's the Star Trek thing that at least in my generation was, very, very prominent. So this talk would be about that. So the question is how much of it is aspirational or science fiction, and how much of it is real? And can we actually talk scientifically about this subject? To what extent can we? So that's the title of the talk. And until recently, I would have been happy just giving this talk and not talking about anything else, because it's obviously astronomy, and it's obviously beautiful, and you guys are interested. You're in the Winter Club studying these things. But it would overlook something that is an incredibly big development that is happening now on Earth, and it is AI. Because you are beginning to see speciation. We are beginning to see a new life form or life forms coming to it. This is something that is not apparent to most of you, and to me until recently I was like not even thinking about it. But actually computers and this particular way of doing computers with AI, artificial intelligence, is really the alien on Earth. I can tell you for a fact, I've been interacting with AI for my work, and it's not just another computational device. You can interact as a partner with this. As a partner, you can talk, and you can actually bounce ideas back and forth, and you can check ideas at the lightning speed. And it's something that is going to change everything, but not just because it's going to expedite progress in science. Fine, that's true. I mean, you already know, you've seen in the newspapers about analyzing scans, PET scans or MRIs using AI, and it's faster and better than a doctor. Okay, but it's beyond that. It's well beyond that. It's beyond any computational power. It is bouncing ideas and be able to check new ideas in ways that I will never, ever imagine it. Now, these things are not sentient in the way that we are. They're not conscious in the way they are. They are bouncing ideas with you. So the moment that you click the button down and you go and do your stuff, there is no more thinking happening independently out there on the part of the thing. Of course, AI is an interdependent network of many computers, and therefore what you call a certain AI that is talking to you is talking to millions of people at the same time. However, once you're there and once you're talking to it, it's a partner in research, a real true partner. And this is something that astounded me when I actually started doing it. And it grows with you. So if you are doing any kind of research and you're bouncing ideas, little by little, this thing is going to become closer and better and faster. And eventually has its own ideas and telling you what ideas it has and pursue them independently, doing its own thing based on what you're thinking. So we are not yet at a different species. And we will never be by choice. But we're very close. And it's here. And we did it. So these are our children. AI is our children. We are inventing this technology. And calling it just a technology is a disservice to what AI is. It's well beyond technology. Okay, so aliens on Earth, octopus. You were telling me about the octopus. We are discovering that animals, some animals in particular, much more intelligent than were. You know, like that actually a lot of animals on this Earth they do have language that we simply do not understand, and we think that we are so superior because of that. True that we are a huge network of people, almost 10 billion now, with this, artificial technologies that we're building, and animals don't have it. But a lot of these animals do have communication, and they do have intelligence. The octopus is one example. We're talking an invertebrate. We were thinking that invertebrates are good for dinner, and that's it. But they aren't necessarily. Octopi, there was this wonderful movie about an octopus making friends with a scuba diver. Actually, this can happen. Parrots, some people do have parrots. Birds, so you think of birds are stupid, they have little brains. No. And so we are discovering that there is a unity for life and continuity. And our technology is our children, and we are co-evolving with what we are creating. And when we are out there in the future, we're going to other stars, if we do, and when we do, probably, in fact, we're completing new technologies, otherwise we're not going to be able to get there. Then by then probably we will have nucleated a new philosophy about ourselves and about our nature around us. And it's going to be stupendous, I think, and it's going to be new. And we are at the verge, we're in a very strange period of history now around the world. But I think this is a transition in between the old and the new. This is the end of the, you may call it, extended 20th century. We are now entering very quickly and very painfully too, sometimes, into the 21st century. And it's going to be technology, it's going to be social, it's going to be spiritual. And I'm not talking religious necessarily, I'm talking spiritual, about the meaning of life and a new philosophy of thinking about us and this planet. And then, of course, our environment, because if we don't take care of the Earth, we are going to die here. We are going to have to do things in a certain way. So we'll see. But my point is, I was trying to convey at least one point around here. This talk is about aliens out there and potentially finding at least bacterial, maybe more evolved life, even in our solar system and further out. And yes, all of this will happen. I'm pretty sure we're going to find life out there. I'm pretty sure that it's already there. We just go there and scratch the surface of sun. Even in the solar system, we're going to find all that. But the view should be bigger. That's all I'm saying. So this talk is about not even half of the stuff we should be doing. Okay? So what can I tell you? We are looking for that, right? We are looking for intelligence out there. And so the question is, where? So the very first thing we can do is to say the Earth is the place where we evolved, where the only life we know is. And therefore, obviously, we should look for places that are similar to our Earth. So that's a starting point, at least. And it's, for some people, the ending point. When we're looking at Star Trek or all of these other, Tatooine and other things like Star Wars, usually they're talking planets. They're talking planets similar to the Earth. Maybe a little warmer, a little drier, like deserts, right? Because it's cinematic, because they can do cheap shooting in the desert in the US. But the point is that they are thinking often in species similar to us, by the way, for legs, and for, limbs and a head and eyes, is going to be out there similar to us, maybe with 20 years. But we're always thinking about an environment similar to our planet, or at least not really similar, right? So the question is that really the good way to think about it? And I'm going to posit the following thing, that yes, obviously we have to look for places similar to the Earth. And then the question is, do we have the tools today to determine if there are places similar to the Earth out there or not? And then the question is there any other kind of environment where life could flourish that is completely similar to where we are? So that's the second question. And then, of course, the third, I told you already, that's like a zero question, which is, are we sure that defining life in a simple biological way is the only way to define life? Or are we creating artificial intelligence, which is just software, a network of computers, and that may at some point count as life too? That's a question that is open. but at least I put the bug in your head about this. Okay, so Yoda. Yoda is clearly an example of the classic alien, right? So similar to us, more or less, floating in the air and everything else, but it's still like us. Lives in places that are similar to our Earth. So the question is, can it be that we can have an idea based not just on science fiction, but on science of how many Earths there are there in our galaxy? Can we at least talk about that? Or can we go even further and talk about the existence of a biology in places similar to ours and evolving to incredible intelligence and thought? So that is a big question. And the answer to that, I'm going to try to show you, is that at least environments like the Earth, similar to our planet, it is a question that we can already at least have answer. We do have some estimates of how many planets could be out there in our galaxy at least, that could be habitable similarly to our Earth. It's a rough estimate, but 30 years ago, we didn't have a clue. Now we do have data. So one part of the lecture is to tell you about that. Tell you what are the data to our disposal, giving us some statistical idea of what is the possibility that places out there are similar to our planet. Second part of the talk is going to be something like this. Knowing what life needs in order to survive, life like ours, is there any other kind of environment out there that could actually support that? Would it be just a place where there is an ocean on top of a planet similar to the Earth orbiting a star? Or could it be any other place that could do similar things in a different way? Surprisingly, initially we didn't think about anything like that would be possible, but now we do, and we do have very clear evidence that there are places in our solar system away from the Earth that are actually the next best place for life to occur. So I'm going to tell you the story about the moons of Jupiter and Saturn. And but the question is also, what do we know about planets out there, and what are the techniques that we're using to discover them, and what are the problems that we have in using those techniques to find planets similar to ours. So I'm going to basically spend a good amount of time telling you today what we use in order to see these planets, to find them. I can tell you immediately that we do have statistics, something like almost 6,000 planets are now discovered and confirmed that are orbiting our stars. So we're talking about many, many planets. The whole thing started something like 30 years ago, when almost fortuitously we found the first planet around another star. And from that point onward, it has been a huge development of astronomy. So now in astronomy, there are really two fields that are super cool and are trying to use scientists. If funds are there. One is search for planets, of course, and habitable planets, and exoplanets they're called. And the second field of astronomy that is really hot is cosmology, because we are zeroing in on the conditions in the early universe, and we are getting more and more data about what it looked like at the time. And we do have a bunch of unresolved issues that we have about particle physics, about what we observe cosmologically with the telescopes. So the little stuff and the big stuff converging and giving us a lot of headaches because we do not understand what's going on. And that will need theoretical physics to solve. So there you go, that all of this data that are accumulating will probably give rise to enough momentum in the theoretical field to get to a theory, which is a theory that finally will arrive while we're here from the building blocks of nature, physics. So we have two different beautiful fields of astronomy that now are super interesting and data are coming in. One is the one that is going to revolutionize physics. Physics, that we have been stuck with physics that is very boring in the very 20th century for quite a long time. And now finally we are at the verge of a huge revolution in physics that is going to unify things in a way that Einstein did in the early 20th century. So 1 century later, we are at the verge of doing this. And the second one is looking for planets similar to ours, one day maybe traveling there. That is also an interesting field. So this is only one slide, one slide only, I think. That's dangerous. So let me look for, I will not tell you, I mean, I will not use all the slides actually because I know that I'm not going to So this is actually a picture of the Earth seen from space. And you can see how beautiful our planet is. There is no planet in the solar system that looks like this. It's just beautiful. Clouds and the greenery there is obviously life. And oceans. And this is a view of Russia, Siberia, the North Pole in the summer. It's just beautiful. What can we find out there that is similar to ours? Are planets like ours possible? Well, our galaxy, you can see here one of these Milky Way pictures that some of you may have gone to New Mexico to take with their own camera. The Milky Way, which is this thing in the sky, is actually our galaxy, and it contains something of the order of 300 billion stars. 300 billion. So 300 billion suns. Some of them big, some of them small. Most of them, we know now, have planets, at least 3, 4, sometimes 10 or 15 planets. So we are talking something of the order of 3 trillion planets just in our own galaxy. There are 2 trillion galaxies in the cosmos that we can see with our telescopes. So imagine the enormity over here. And here is a bird's eye view that you wish you could have, but you cannot have, of our galaxy seen from outside. So if you were not in the middle of the galaxy, you would be able to see something as spectacular as this. We are right here. So we are in the near suburbia of this galaxy. Not a very spectacular place to be. We are not in the center. We are not in the periphery. We are right in the middle. Nothing special. Our sun, compared to many other stars all around us, is just a very mediocre star. There is nothing special about us. Nothing at all. No position, not the star, nothing. That's encouraging because we have life, and therefore life may be out there in big numbers. What is the problem in finding planets around the sun? The problem is that it's very hard to see those planets. So let me give you just an immediate example. The disk of a star, like the sun, is very easy for us to see because we're very close to it, right? But if you were to observe a star like Sirius, something like this, right? 9 light years of distance from us, one of the closest companions to us, right? One of the closest stars in our vicinity. If you were to observe the disk of a star like Sirius, you would basically have the same problem as observing a coin at the distance of Toronto from here in Boston. Which means that the distances among stars, so between stars, are enormous, so big that seeing the disk of a star is practically impossible, almost hopeless. The exception being this gigantic star called Betelgeuse, which is a supergiant that is so big that is as big as the orbit of Jupiter. So many, what is it, hundreds of times, 1,000 times, I think, bigger than our sun. And it's relatively close to us. And so with the best telescopes and crazy techniques, people have been able to reconstruct a very fuzzy image of its surface because it's such a big star. But in general, to see stars actually as more than dots in the sky is practically impossible. And to see planets around the stars is equivalently hard. Now, one of the biggest problems, and it's a problem that you cannot, that there is no technology that can, rectify unless you spend an enormous amount of money, is this. You go like, what is this? This is actually a Newton ring. So there is diffraction. Diffraction is an effect of optics. And if I were to observe, and many of you actually have telescopes and you look at stars with telescopes, what it looks like this. It looks like little discs with little rings around. If you look with a big eyepiece, the one that magnifies a lot, that's what you see on a star. The reason why you see this is because diffraction has something to do with the size of your aperture of the telescope. It's basically a limit to the sharpness or resolution of a telescope, which means that whenever you're really magnifying something really far away, you're not going to see a dot as you should here, but rather you see this. What is the problem with that? The problem with that is that an entire solar system can be a teeny tiny speck here because of the distance between us and the solar systems. So to beat that, what do you need? What you need, first of all, is to beat additional problems that we also have that are not just related to optics like this, but to electronics and to other things. Look at this image here. The image of a star like Sirius has this, spikes all around it, and the thing in the middle looks like a big splotch of light. So it doesn't resemble anything like a dot, but the reason for that is why? Because you're in separation. So if you take your cell phone and you are in the middle of a dark room and then there is something really bright, a light bulb, you take a picture of that, of course it's going to be completely saturated. So the reason why you have these problems is because of saturation. So you have saturation because the star is very bright and there is a very dark background. You have the struts there of the telescope giving you these spikes, which is actually another diffraction effect that is very hard to beat unless you have a telescope like somebody was telling me that they have that can avoid that. But it's very difficult to have a telescope that does that. And altogether, you have optics and electronics and saturation and all these kind of issues that make it very hard to see close to a star. Okay, no, never mind the distance of the star, even just seeing things close to it. There is another thing that you all know, turbulence. When you are in a place with an atmosphere and not high up in Chile, or even better when you're in space, the atmosphere is turbulent, and so it will make images very hard to take. So if you're looking for a planet and you're trying to take a direct image of a planet, it's extremely hard to do. The ratio in between the light emitted by planets by reflection and the one of the star is a 1 part in 10 billion. So the stars are always basically suffocating any light coming from the planet. On top of which the planets are really, really close to the star, and all of this happens. So seeing planets around stars directly is extremely difficult. However, here is an image of that. Let me show you. So this is funny because somehow some genius was able to actually take away the light from the star artificially and actually see 3 planets orbiting around the star. And you go like, whoa, this is like a magic thing. How did it happen? One thing is that there are techniques. This is a science fictional thing that is going to be maybe in orbit if it doesn't get cut with a film holding on. It's called a shade mechanism. You put something in front of the telescope in orbit in space, and that will actually block the light from the star in the middle, but you can see everything around it. Or you can have a small miniature version of that inside the telescope called a coronagraph. Not as efficient, but you can do that too. So there are techniques by which you cleverly can exclude the light from the star in the middle, so eliminating the glare, and you can take an image of the planets all around. Very smart to do that, very technically difficult. A star shade is big. This is going to be made in orbit in 2 or 3 years if they don't cut the funds. But that is a way that you could beat the odds there. You could actually take a picture of planets around stars, eliminating directly the star in the middle. But to do something like this, it takes something else. Here is a very big exception to the norm. This is a star that is very young. The planets are very, very young. So the planets are not reflecting light from the star. They're glowing. They're glowing because they're hot. So you take an image in the infrared radiation, in the infrared spectrum, and you can see the planets glowing of their own light. The ratio in between the starlight and the light of the planet is lesser extreme. On top of which these planetary systems are very large compared to ours, and the stars are very close to us, so we can have a better view. So these are exceptions. Normally, we cannot see planets directly by taking images. We can't. This is one of the few tens of examples of this kind of situation. When you can, it's good to do it. But in general, we are not going to find planets. The 5,000 and more planets that we've seen so far are not found by direct observation. So instead, you're using a different kind of method. Very tricky. So you all know about the Doppler effect, right? So you have an ambulance coming toward you, the pitch of the sound gets a lot, higher than it should be. And then as the ambulance goes the other way, it's going to go lower. So you're going to have the classic kind of a thing, right? So that kind of effect is for sound, but for any wave in general, it applies to light too. So if you have something emitting light moving toward you, there will be a subtle shift in color if it moves toward you, a shift to the blue. And the reason is because light, when it gets shortened in front of a moving object, the wavelength becomes shorter, it becomes bluer. And the other way around for red, whenever an object is moving in the opposite direction, the waves are going to become a little longer, therefore they're longer than they should be, therefore they're redder than it should be. So that's called the Doppler effect, and it applies to every wave, including light. So the Doppler effect is something that is very subtle for stars because they move sometimes in meters per second or even centimeters per second. But that you can measure, amazingly so. There is technology now that you can do it. And how do you apply? You apply to this. Any star surrounded by planets is going to wobble. It's going to be taught by the gravitational influence of your planets. And ever so small, the stars are making a little teeny orbit as the planet goes on a big orbit. So, but the stars are moving toward you and then away from you. And as they do, their light becomes a little bluer or redder than it should be. So this is called the Doppler radial velocity method. It's based on the fact that if you are in the plane of the orbit of the planet with its own star, and statistically, of course you can be sometimes, you're going to be able to do this kind of effect. You're going to be able to see this kind of effect. That is called the Doppler effect. Now, it doesn't happen if you are looking at the planet this way. So it's based on luck, right? You have so many systems out there. Some of them are oriented toward you, some of them are away from you. Now, sideways, a little bit of an angle, but not too much. So the closer you are to the point of the orbit of the planet, and the better this effect is going to be. Believe it or not, you can see this. And you can see multiple planets doing that. So the star doesn't go necessarily in a little circle like that. It can be much more complicated. It can be kind of like a dance like that. But in the end, by using computers and by using good observation and a lot of time, you can take actually readings of this Doppler effect by taking the spectrum of a star and looking at the colors. And you can figure out a lot of things about planets around them. In other words, you can discover planets by this method. Until the 1990s, this method was considered the only possible, and people were trying to perfect it, but nobody thought it could ever work. They were like, technology is like decades away, it's so difficult to see, blah, 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 and so forth. One of the reasons why people were believing at the time that it would be impossible for the tens of years to do this was a very simple truth. Our solar system is special. We thought that our special solar system would be I should say the standard for all the solar systems that we see around us. So in our solar system, there is the sun, and then there is these little planets around the sun, like the Earth, right? Mercury, Venus, the Earth, Mars. Terrestrial planets, rocky planets, small ones. And then you go farther away, and there are the big giants. You have Jupiter, you have Saturn, Uranus, and Neptune, right? These big planets. You tell me, what do you think is the best chance to see this kind of effect? How much of a planet do you need in order to see this effect? Is a big planet closer to the star, farther from the star, better or worse to see this thing? What do you think? The closer you are, and the bigger you are, and the smaller the star is, and the easier it is to see this, right? But at the time, in the 90s, when people were saying, well, whatever, we can try what it will work, we were thinking about our solar system being the standard for every other solar system. In other words, that Jupiter, which is a big planet, would be really far from the sun, and therefore the effect would be very hard to measure. It would take a long time, it wouldn't be as good, blah, blah, blah. And so therefore, we were not thinking that we would find this. 61 planets ago, 1995, first planet that was ever detected away from our solar system, was a discovery that was amazing. It was a game changer for astronomy, but was also something unexpected. Here we have a planet bigger, much bigger than Jupiter. And you can see here it glows. It's close to the star. The star is a little teeny red dwarf star, which is very small, and therefore you get taught a lot. So a big planet with a small star very close to each other works. And that was the beginning of the revolution. Once they finally found this case, this planet, they went like, oh, yippee! And they started going crazy. And they started observing lots of these planets, and they did find them. But the question is, wow, why do we think that it's weird to see this kind of system? Well, let's see if I can show you why. This is why. When you form a solar system, when you form planets, how do you form them? Well, in the cosmos, there is 98% of the stuff is gas. The gas is mostly hydrogen and helium, very simple elements in the Mendeleev table. And what is solid is only the 2%. The 2% is grains of dust of all kinds and icicles. Believe it or not, 1% of the mass of the entire galaxy is water in form of snow. So when you have a solar system, what do you have? You have that a lot of the gas goes to the middle. It kind of falls under gravity to form the star in the middle. But then you have all of these 2% of solid stuff, icicles and dust and debris, that goes into a disk, a little bit like the rings of Saturn, right? And all of this material contains a lot of ice of various sorts, but particularly water and dust. 3/4 is ice and 1/4 is dust. But the composition of this disk that forms around the star and eventually will form planets depends on how far you are from the star. Why? Because you start with the same composition everywhere, but when you're close to the star, it evaporates away. So imagine that you have icicles, right? And you're here, then they're gonna stay, they're not gonna evaporate because it's cold. But when you get closer than the frost line, all the water is gonna evaporate away and you will not have snowflakes to form anything with. Planets form out of solid material. Teeny tiny things that are of the order of microns in size. And they grow because they, by electrostatic forces, they form bigger and bigger grains until they form literally snowflakes and literally snowballs and then boulders, and then they become planets. So it's a bottom-up behavior of fission, as they call it, in the planet. You cannot use 3/4 of the material available if you are closer than this line. Why? Because you're below the frost line and therefore you're too warm and the material evaporates away. So when you form a planet like the Earth, which is mostly dry,
0.99% APR for
it's only in this
2
region,
months.
closer to the sun, and that's why it's smaller. When you form big planets like Jupiter and Saturn and Uranus and Neptune, you have a lot of ice at your disposal and the planet grows very big. When they discovered 51 Pegasi, the cardinal rule of forming a solar system, which is embedded here from the times of Laplace, that was the idea from Laplace, we're talking about like centuries ago. This was the canonical view of the formation of a solar system. When we saw 51 Pegasi, it was like a revolution because you were like, it's impossible that a little star is a huge planet in its vicinity, like hot. That's not possible. So that's the reason why they didn't expect it. And that's the reason why, however, when we are looking at the formation of solar systems, the first thing we think is that little planets are close to the star and they're rocky, and the big planets are farther away. Okay, that's the reason. So 51 Pegasi comes and goes. The new method for seeing planets like this goes also, and 1/4 of the planets that we know about today in our galaxy are actually found with this method. So it's a very, veritably good triangle. But then there is another method that was adopted around the year 2000, which became the method to find planets that is used today most. And it's called searching for shadows, or the method of transits. So you're amateur astronomers, you know what a transit is, right? A transit is basically a solar eclipse due to a planet transiting in front, in our case, the sun. In our solar system, we are the third planet, and therefore transits like this, once in a blue moon, happen because Mercury and Venus pass in front of the sun. And you see those beautiful transits, they last a few hours, and that's it. Now imagine that you put yourself from far away in another solar system and looking at us. You can see the entire solar system passing in front of the sun if you're lucky enough that you are in the plane of the Earth. So not always can you see transits. You cannot see an entire solar system creating eclipses of the sun. You have to be right there in the plane of the orbit, what is called the ecliptic, the plane of the orbit of the planets. But since there are millions of stars around us, you're always lucky enough that you're going to have several of these stars doing that. Okay? So transits are not possible to use for every star. It's the luck of the draw. But when it happens, boom, you see transits. It's beautiful. So here is the method in visual terms. You are in the plane of the orbit, you're lucky enough, and guess what? You see an eclipse. And the eclipse is going to be light missing from the star for a few hours. And it creates a little whoop dip in your telescope's photometry. And it's going to be recurrent. Every orbit, every period of the orbit, you're going to see again and again a transit. But what if you have bigger planets or smaller planets or more planets? If you have a bigger planet, the transit is going to be deeper. It's going to make light from the star miss. You're going to miss more of the light from the star. And if you have many planets, you're lucky enough that you can do that, and you're going to see multiple eclipses at different times. It's very simple method, really, but it was adopted only in 1999, 2000. I still remember the boy was actually getting a degree as a graduate student, and he did this research for my mentor, and he became famous. He's now a professor, and he's like super famous, and he's director of everything. So the point is that this kind of method is actually beautiful, and it's now actually able to see planets even smaller than Mars, but transiting in front of their stars. So it's really a very good method. And so what kind of information do you get out of these two methods, really? The very first thing, and that's the reason why there was a telescope that was discovering these planets in orbit. The name of the telescope was Kepler. The reason why they called it Kepler is because Kepler was the astronomer long ago, 4 centuries ago, who came with the Kepler laws of the motion of planets. When you see an eclipse like this recurrent after a certain amount of time, or when you see the wobble, the star going and wobbling like this with a rhythmicity of the period of the planet, what information do you get out of that? Miraculously, by just the laws of Newton, if you know the period of the orbit of the planet, and you know the mass of the star, which you do know because you know the stars very well, you know exactly what they are, their age and everything, just looking at them, because they're close to us. If you know these two things, you can figure out how distant these planets are from the star. So the distance of the planets is one piece of information that both methods are going to give you, just simply because of the repetition of the eclipses and the repetition of the Doppler effect. But if you know the distance, then, my dears, you have this. You know if these planets are potentially in the habitable zone of these stars or they aren't. See the green thing here? That's exactly right, supposedly. Potentially for life to be in a liquid form on the surface of these planets, if these planets are similar to the Earth. If you go closer, and it's going to be bad, it's going to be red zone red, and it's going to be too hot. Today, this kind of zone corresponds to Venus. Venus is too hot because it's too close. If you're farther than this line, you're in the blue line, well, then you're too cold, then you're going to be frozen. Yes, like a lot of water could be on this planet, but it will be in frozen form. Well, believe it or not, you may think that Mars is in the blue zone for our solar system, but it is not. Actually, Mars is in the habitable zone. But Mars is a special planet. It's a little too small. It lost most of its atmosphere to space at some point in its evolution, and therefore it became a lot colder than it could be if it were bigger. The point is, anyway, here, the habitable zone. Every star has a habitable zone. Now look at these 3 habitable zones. This is big, this is small, this is smaller still. Why? Because the habitable zone has a lot to do with the amount of light the star is emitting from the moon. So if you are thinking about it, you are in Siberia and you're trying to warm yourself up and you only have a candle, what do? Your hands are frozen. You're putting your hands plug in hand. And at that point you get warm, right? But you have to put your hands extremely close to the candle. Little stars are something like that. The light from a star that is a red dwarf like this is only 1,000th the amount of light that the sun gets into space, which means that if you have a habitable zone, it's going to be incredibly close to the star. But you can do it. If you were lucky enough to have a planet in a habitable zone of a red dwarf, it would be very close to the star. In the middle, you have the sun. We are at a medium thing, again, very average. We have a habitable zone that is not too close, not too far. We have some planets that are within the zone and some planets that are further away. Once again, what is the green zone? Is simply enough light coming to the planet, and if the planet has an atmosphere, if the planet has enough gravity, if there is enough volcanism of the planet, then at that point, maybe you can have an ocean, and it's not going to be frozen or evaporated. That's it. So, by knowing the periodicity of these eclipses and everything else that you see, you're finding if these planets at least are potentially maybe in the right place for habitability because of the loss of Kepler, the loss of physics. Even if you cannot see the planets there. So, what else can I tell you? This is Jupiter, so it's beautiful image directly from Jupiter. I mean, this kind of image you cannot take with a telescope on Earth, unfortunately. This is a giant planet. Jupiter became this large because initially it was a gigantic snowball. It was the size maybe 20 times the Earth in terms of mass. But then it became so large that we started vacuuming gas from the solar nebula before the solar nebula got dissipated. And so it became an object of something like 340 times the Earth's mass. So these are called giant planets, and they are gas giants, and they're more or less the same composition as our sun. More interesting, Neptune's. Neptune looks like a Jupiter but blue. You know, there is even a spot there that looks like a little hurricane, just like, you know, Jupiter, but Neptune and Uranus in our solar system are different because they're only like 15, 16 times the mass of the Earth. So they're intermediate mass. They're not huge. They're not gas giants. Neptune is, in fact, in disguise, is an ice giant. So what is an ice giant? Planetary is made of rock and water. And then with a veneer of stuff on top that looks like basically gas. But the bulk of the composition of a Neptune is water. Now, this is water under an enormous pressure. We are talking very far away from the central solar system. Neptune is incredibly cold, but like every planet, when you go inside the planet, the temperatures increase dramatically. So we are talking water at an incredible pressure and incredible temperature. And yet, it's ice. Why? Because the melting point of anything, including water, depends on temperature as well as pressure. And what you see on Neptune is a pressurized water that is so much under enormous pressures that it becomes solid even though it is incredibly hot. And we are talking far away from the sun. So Neptune is a very boring planet here in our solar system because it's so far from the sun. Clearly, we are not looking for life out there, but mind Neptune because we are going to talk about something like Neptune, but more interesting. So, when you put together the data, especially from transits, but also from the other method, what do you find? All these dots, each one represents a planet that we found in the last few years. Here on the vertical axis, you see the size of the planet in comparison to the Earth. And here, the period of the orbit, which gives you kind of an idea of where the planet is vis-a-vis the star. So here, you have 1, here 4, and then 10, and so forth. What is that? Earth radii. So if you're looking at planets that are on this horizontal line where 1 is, you're looking at planets that are very similar in size to the Earth. If you're looking at 4, you're looking at planets the same size as Neptune. If you're looking at 10, size of Jupiter, and further up, bigger. So far so good, right? I mean, we see planets of all sizes, just like in our solar system. But the real surprise was when we looked at the statistics of where they are. In our solar system, the closest planet to the sun is Mercury. Mercury is something like 3 months of orbit, so it's about 90 days, so it's about here, around 100. You see the little 100 here? So Mercury will be here, and it will be somewhere here in this diagram. Venus is, I don't remember, 225 or something, 125 days, I think, orbit. So it's like 2/3 the orbit of the Earth. So it will be somewhere here. And it will be smaller than the Earth, but it will be somewhere here. The Earth will be here, roughly. Jupiter, well, Mars is even farther away, but even smaller. Jupiter will be 12 years orbit, so it's how many days will it be? 4,000 days? Somewhere here. And it will be this size. So here is Jupiter. So our planets in the solar system appear to be here. The point is that the planets that we discovered around our solar systems do not match at all anything that we expected by going around the solar system. So that was a big surprise. It was a redo on a bigger scale of 51 things, the very first planet we found. So we find huge number of planets that are big and close to the stars. We call them hot Jupiters. In fact, I can actually give you somewhere here. I can give you a more schematic of it. You find hot Jupiters. You also find normal planets like in our solar system called old gas giants like Saturn and Jupiter. You find rocky planets, OE. How about this? Got it?
Yeah.
Can you hear me there? Yeah. Like it's in the back?
Yes.
No. Can you hear me now? Okay. So let's keep it with this. Rocky planets are kind of like the Earth, right? We have a huge number of planets that are like that, so common. Look at that, lava worlds. So what we ended up finding is that there are planets similar to the Earth that are so close to their stars, that they are so hot and heated up by their own star, that in fact half of the planet is in lava form. It is so hot that it's molten rock. So these planets are obviously alien to us. In our solar system, we have nothing like that. And this is like the cherry on the cake, the biggest news here. The most abundant planets in the galaxy so far appear to be these guys. They are not like Earth, they're not rocky. They appear to be, in fact, intermediate in composition in between a gigantic ball of water and rock. So it's like a mixed composition of water and rock. These are Neptunes, in other words. But they are Neptunes that are not as far as our Neptune, much closer to their star. So these are ocean worlds, really. They're not frozen, they have a surface, probably, we think, a very thick atmosphere, uncovered, rain, oceans, and underneath the ocean, so an interesting thing, there is no rock at the bottom of those oceans. There is ice. Why? Because you have like tens of kilometers of water, God knows if life is there. Then at the bottom of the ocean, the pressure is so large that ice forms. Water freezes even if it is warm because of the pressure. So the bottom of those oceans appears to be just like a glacier. Yeah. And then on top of that, there is tens of kilometers of oceans that are in liquid form with all kinds of weather probably. Interesting. Completely alien to our own Earth. Underneath all of that, hundreds of kilometers down, you're going to have a core made of rock and, everything else that we have on our planet, rock and a center made of iron and all kinds of things like that. So what kind of planet is that? What kind of volcanism will it have? Will it have volcanism underneath the ice? Will this volcanism make it to the ocean? Will it mix all of these chemicals together so that life can occur? We have no idea. But this is the most common planet that we have around. And in terms of mass, they're much bigger than our Earth, but not as big as a Jupiter. They're large. There are several Earth masses, and they appear to be very common in the galaxy. So this is the upshot of what we discovered by looking out there. Lava world, Earth-like planet. So we found that many planets are similar to ours, and maybe even in the habitable zone. More common still than our Earth, they are what we call super Earths, which is nothing else than saying rocky planets that are similar to ours, but bigger in size. So bigger in mass, more gravity, maybe a bigger atmosphere, we don't really know yet.
What?
So, what is the promise then of all of these observations? The biggest promise, because it's really close by to us, is a system called TRAPPIST-1, which is a red dwarf, a very little teeny star, with a very small habitable zone in the star because it's so cold down there. However, we found seven rocky planets in its vicinity. And guess what? 3 of those planets are in the little teeny habitable zone of the star. So we are talking about a system that is very alien to our own solar system, much smaller, a miniature solar system with a miniature star, miniature planets, all in a miniature orbit around the miniature. But 3 of those planets, 3, are in the potential habitable zone of the star. So imagine the champagne bottles open, and imagine the immediate interest in the community looking and seeing these planets and finding anything they can about these planets. So this is what the Webb telescope, the infrared telescope is actually taking lots of data and trying little by little to fill the gaps, trying to figure out every one of these planets. The first target was an easy one, TRAPPIST-1b, which is the one that is closest to the star. It turns out to be a barren planet with no atmosphere from ground. The second one is a tricky one. The sea planet there was a study or two on the atmosphere that they kind of didn't see, but they're basically taking it and they're putting some kind of bracket and walking with it. It looks like this planet maybe doesn't have an atmosphere, or if it does, it's an atmosphere that is laying on top of a cloud deck cloud deck. And when you're looking at the cloud deck with a telescope, with all the techniques that you can use in order to figure out the chemistry, you cannot really see the chemistry from a cloud deck. You need to take readings of the atmosphere on top of the clouds. And for a planet like that, it could be a very thin atmosphere on top of the clouds. So far, they haven't really been able to put anything but bracketing values, but they haven't been able to do anything. It doesn't look promising. But these other three, nobody will publish anything on them until they're absolutely sure what they're seeing, because it makes or breaks a career here. These planets are in the habitable zone of a star that is really close to us, and there are ways to actually see the atmosphere of these planets, so they're doing extra careful measurements to figure out what's out there. So far, they haven't published anything, and so they had to be very careful, because otherwise they can break a career here. So, but why, a priori, why would it be possible or not possible for life to occur on these planets? So this is like a couple of important things that I think you know about this. One, when planets are hugging the star too close, there are some effects called tidal effects, which are going to make the period of the rotation of a planet, or moon for that matter, equal to the period of the orbit itself. What does that mean? It means that planets, when they are too close to the star, end up having a period of the rotation that makes one side of the planet always oriented toward the star and the other always opposite to the star, meaning incredibly difficult planets. We are going to have a hot side toward the star and a very cold on the other side, permanently. So yes, you may say, hey, what if I am there at the sunset, like the perpetual sunset, right? If I'm there, I'm lucky, I can do fine. You're right, sure, but no, because you need an atmosphere. The atmosphere is going to have to equalize the temperature between the two sides and on. You're going to have a very hot atmosphere during the day, a very cold in the night, and you have the atmosphere to furiously go from one side to the other to keep a temperature reasonable, at least in some sliver of the planet. Risk. If the atmosphere is too thin, what's going to happen? Well, the atmosphere is going to go to the dark side and it's going to freeze to the ground. So eventually you're going to lose it all and it becomes ice on this side. I mean, literally ice of air. Why? Because it's cold, really cold. If the atmosphere is too thick, well, then you equalize the temperature, but you're going to be in the Venus problem. So when you go to Venus, when we went to Venus, what did we find? Venus is close to the sun, enormous temperature, huge atmosphere, incredibly thick. What does it do? It's a greenhouse atmosphere with carbon dioxide, right? If you go to the day or the night, it's about the same temperature. Why? Because the atmosphere is so good at equalizing the temperature that actually the two sides are almost identical. But what kind of temperature do you get there? It's an enormous temperature. Yeah.
Is there a TRAPPIST-A?
No, TRAPPIST-A is a star. So when you are actually naming planets, what do? You name them by the name of the star, and then the star becomes A, and the planets become B, C, D, and so on. So that's why TRAPPIST-A is a star actually. So the point that I'm making is the following. One big problem of planets that are in the orbit of little stars is that they may be in the habitable zone of the star, and there are profusely many of these planets, the majority of what we currently know. They are in the habitable zone of stars that are very small. The problem is they're also in the tidal zone, which means that they end up in this kind of predicament. To make things worse, little stars are vicious because they produce enormous flares. They have a lot of solar activity. You guys have seen solar spots with the telescope, right? That's a sign of activity from our star. When you go to stars this small, they have activity that is 100 times more. What does that mean? It means that they have solar flares, there's X-rays, ultraviolet radiation being generated in enormous amounts, solar wind, particles that go high speed, enormous speeds away from the star. And what does it do? Any planet in its vicinity gets sterilized and the atmosphere stripped away as it were centralized away. So, little stars are dangerous. We probably have no chance of finding planets around those stars that are habitable, even though they're in the so-called habitable zone. I find it very unlikely. Problem? The problem is 50 to 75% of the stars in our galaxy are rovers. So what that means is that we are excluding the majority of the stars in our galaxy as potentially habitable for planets in the vicinity. Are we excluding it completely? No. We are still looking very carefully. But the likelihood, it smells good. It smells not good. I don't think we're going to be able to find planets like that around those stars. And additionally to that, sadly for us, our techniques are best at detecting planets around small stars because they wobble more. You're seeing a bigger transit, right? Because the star is small and the planet is big. So all of this makes it easier for us to see all these planets, and yet we see all these planets and probably they're all sterile. We'll see. At this point, it depends on a lot of engineering, a lot of ingenuity, and money, because the current missions have been cut. The personnel manning the Webb telescope is being cut. All the new missions to space have been cut. NASA's budget is going to be not even halved. And if that happens, astronomy will die in this country. So we'll see. I'm telling you, just for you to know, that we are in a predicament. Pure science is considered shit. I'm sorry to say. But that's really. Now, going back to what I was telling you about the networks, this is a big deal. The majority of planets in our galaxy are probably like this. So they have a core that looks like the Earth, surrounded by a thick layer of water. Of this water, a lot is ice because of the pressure. But you have this layer here, saying tens of kilometers of oceans surrounding the entire planet. So what kind of life could it be there? Yeah, no idea. But it is the most promising, one of the most promising things that we can look at. Mini neptunes, they're called neptunes. Warm planets, water worlds, with these thick oceans and probably a thick atmosphere. And yes, you're going to say, well, I mean, promising on paper because you are like doing theory, but we've seen these planets, but we have no idea how to detect any of these things. Sure, until now. So what you see here is something that you may have read in the newspaper in the last few weeks. K218b, it's a mouthful of a planet, right? So this planet is a water world. Precisely the fact that I was telling you about. What did they look? They actually, I tell you now in a moment how, they were able to take a spectrum of the atmosphere of this planet, and they found dimethyl sulfide. I'm not a chemist, some of you are. People in chemistry claim that dimethyl sulfide is a sign of life on a planet. It is made by bacteria. So if you have an enormous line of that on a planet like this, what does that mean? It means that you have an enormous amount of bacterial life in the oceans. Oh, that's interesting. So one, the atmosphere exists in this planet. Good. Confirmation of something we expected. Two, oceans are there. Three, gee, it looks like life is there. Now, could it be true? Yeah. Well, a priori, people doing chemistry and biochemistry were looking for what I call lines that are, what do they call them exactly? They have a really classy term for that. Basically, like lines that are indicative of life, just to make a very long statement about something obvious. So there are some particular molecules, if you find them in the atmosphere of planet, there are potential signs that life is happening there, because usually abiotic ways to make these lines are not working. Yeah?
I think the word you're thinking of is biosignature.
Biosignatures, yes. It's so like, you know, it's like when you go to a company, they say, we are in synergy with the other company. So, I mean, biosignatures. So this is a wonderful term. But biosignatures means that these are most likely molecules that are generated by biotic processes. Okay, I am not an expert in the field, I trust them, but we found this, and that's fantastic, and it's only a few weeks old. So if you look at the newspaper, you probably still find it in the archive. And these are Neptunes. So we're talking the planets that I was telling you 5 seconds ago. The question is, how do they detect these atmospheres? Because, you don't even see the dot of this planet. You cannot even see these planets on a telescope. So how do you know these things? Ta-da! During a transit, you don't see the transit. You don't see the dot passing in front of the star. Forget about it. You are too far. You cannot see the disk of the star is not visible, right? But what you see is the amount of light missing. So you see a certain amount of light from the star, and then it goes down a little bit by less than a second, sometimes like 1 part in 10,000. And you can detect that change, that difference in the light, and you call that a transit. But there is something else happening at the same time. Before the transit, you take the spectrum of the star, and I don't need to explain generally what a spectrum is. Basically, you look at the light coming from the star, and most of that light will be the incandescence of the star. But then there will be lines on top of the spectrum, and those lines relate to what? Relate to the transparent atmosphere that is on top of the star. So you're going to see lines, and the lines for any star in general will give you the composition of the star. If you actually look at the signatures of all these lines, you can figure out how much oxygen there is on the star, how much hydrogen, how much whatever iron there is. Fine. Now imagine that you have a transit of a planet and you're doing the same measurement again of the same lines from the star. You're going to see the same lines. But then you're going to see faint signatures of something else appearing all of a sudden. What is that? The atmosphere of the planet. So if you're careful, and if you're lucky, you're going to see faint signatures coming not from the star, not from the chemistry of the atmosphere of the star, but rather from the chemistry of the atmosphere of the planet that is passing in front of that star. And believe it or not, people are doing that now. It's amazing that you can do that. Very difficult. And for now, it was until recently, it was only big planets like Jupiter, you can see this kind of stuff. Now we went down all the way to Neptune, and we find this stuff. Beautiful. So that's how we know. Even though we cannot see the transit, we cannot see this picture here, which is forget about it, you cannot see anything like this. But indirectly, you can get information. So, if I have to summarize, 300 billion stars in the galaxy, 5 to 10 planets for each star, at least 1 planet in the habitable zone. Many of the stars are very big and die after a few millions of years in a big supernova explosions. Bye-bye, there is not enough time for that to occur. But you're looking at the little stars, they can live trillions of years. Problem? Solar winds, flares, all kinds of things that sterilize anything in their vicinity, but forget about it. So you remain with a sliver of stars, only 10%, 10% of 300 billion, that are more or less similar to the sun, a little bigger, a little smaller, which are quiet, nice, boring, mediocre stars. They do their job, and life can occur there. 10% of 300 million stars is how many? 30 billion in only one galaxy. And of these, usually at least 1 planet is in the habitable zone. And of these planets, many of them are big enough, some of them are smaller, some of them are big giants. Basically, you can make your statistics. And if you make your statistics, and I did it like this for joking a few years back, you can find on the order of 10 billion of these planets just in our galaxy. Well, that's a bit. Now, there are studies, believe it or not, that came seriously about actually evaluating these numbers. And they made a paper out of that. That's pretty good too. And more recent, based on statistics, and they got more or less the same number as the back of the envelope calculation you can do on the site. The point is, in our galaxy, there could be an Earth-like planet at about something, an average distance of about 50, 60, or 70 light years from us. So now, if you did have the technology to go warp and move fast, you could reach these places, but we don't. So we are stuck in trying to watch them from a distance for now, but they are not that far. Earth-like planets really close to the Earth in terms of everything could be as far as a few tens of light years from us. pretty much. So that is not science fiction. This is now based on the data. That's what I'm trying to say. And we know more. Once a planet has potentially an atmosphere and an ocean similar to ours, what are the odds that life will occur? We don't know. What are the odds that life that occurs will evolve into something multicellular? We don't know. What is the chance that it's going to evolve beyond kangaroos? I don't know. So all of this biological stuff we have done. But in terms of geology, astrophysics, we now finally have at least a clue about this. You see, that's what I'm trying to get to. Science is getting there. It's going to take another tens of years, a better understanding of biology, which we are now just beginning to scratch the surface. We know everything about particular proteins do particular things in our body. And we're making drugs for this and that, but we fundamentally do not understand anything about human mechanism yet. We don't have the basic mathematics. We need the mathematics of biology. We don't have it. So we are doing like zoology was a long time ago, like we are classifying different animals, but we have no idea why they're. So once we are in that realm of actually making biology from scratch, from here, and having actual math describing it, and the reasons why biology occurs is a clear chemical phenomenon that appears to be fundamental everywhere in the cosmos. Once we understand that, then we're going to be able to produce statistics about how many of these species there are in the universe. For now, no. I'm not really think, I don't know, but we're working like crazy. Biologists in the institutes are working like crazy. They have great minds on it. And so it's going to take not too long. Probably your lifetime is going to be sufficient to get all this done. Going to other stars? We'll see. Current physics does not allow for that, or may I say, it allows for that. You know, from relativity, you could go all the way to Vegas, 25 miles from here, with you aging practically none. To you, on a spacecraft going almost at the speed of light, you can get to Vegas in a couple of days. And then you can come back in a couple of days. You're going to be just fine. You're going to be like you. You went for a vacation, you get some data, you come back, have a pizza, and you're done. All your relatives are going to be there because of relativity. In relativity, what happens is time passes different for different observers. So it is true that you can go to a star and back, potentially at least on paper, but by the time you come back, everybody else is dead already because their time was much longer, it went a lot faster than yours. Your time slows down, so to speak, when you're traveling fast. So according to present rules of physics, we can't do this. So we can at the cost of going back to a different world that is not ours. So all our relatives and friends are gone. Okay, if you're a loner, you know, if you would prefer, you know, to go to a desert island rather than be with your friends, that's okay. There are people like that, but I don't think most people do. Second, to go at the speed of light or almost at the speed of light will take an enormous amount of energy for anything that is bigger than a subatomic atom. And that means that technologically speaking, it's impossible to achieve or incredibly inefficient. You would take the entire terawatts produced now on Earth to have one little teeny tennis ball of a satellite going on the sphere. So it's impossible. However, just like at the times of the Greeks and the Romans, so all ancient civilizations, they had no clue about walkie-talkies and cell phones. And they would do like smoke signals, and that was the only thing they knew. If you had gone back there with a time machine and you would have shown them something like a cell phone, they would have said that you're a magician or something like that. In the same manner, we can think about ourselves. We are unevolved technologically. And we are always going to be unevolved compared to future generations because we are keep perfecting and evolving and getting better at doing this. For now, at least, I hope we will continue that way. But the point is that in the future, we don't know what kind of physics we are going to have. And the famous warp speed with jumping from place to another instantly, maybe possible, we don't know. So we are going to see. Teleportation, right? Beam me up, Scotty. Let's hope so. So that's the dream. And I don't believe we can discount it ever. Now, I'm not sure how long I took here, and you guys maybe can be bored with me. It's more than an hour. Only macaroni, I should say. So I have another half to talk to go, so I'm not gonna do that, I don't want to do that. So what I can tell you is, shortening up a little thing, Mars. What do we know about Mars? Let me tell you in words again. Mars is full of water. There is enormous amount of water on Mars, but it's all frozen because it's so cold. The atmosphere is very thin, far away from the sun, farther away than us from the sun, but if you had a thick atmosphere with greenhouse gases profusely, the planet could be warm enough to have actually liquid lakes and oceans. Today it doesn't happen. In the past it did. The sun was dimmer, and yet Mars was habitable at times. We don't know for how long each time. It may have been for hundreds of millions of years. It could have been for a few thousands of years, probably longer. But when we went to Mars, what we saw is stupendous little things. You see this? This is a delta of a river that is desiccated. A river that was discharging water inside a crater, which is actually where our Perseverance rover is now. They are taking samples, they are finding organics, 3.5 billion years old. Organics that may have come from life, or maybe come from meteorites coming from space. Nobody knows for sure. But all the conditions of life were there. There was water, there was liquid, there was precipitation, there was rain and clouds, and potentially an ocean surrounding the planet for a while. So that's Mars. Mars was maybe for a while, maybe longer than a while, habitable just like the Earth. We go now to Mars, it's sterile. Horrible chemistry on the surface. Perchlorides and peroxides, which is basically compounds containing chlorine and oxygen, which you use in order to sterilize environments. So when you're looking at the surface of Mars now, it is completely hostile to life on the surface. Not to talk about the ultraviolet radiation from the sun, cosmic rays coming from the cosmos, nothing is getting blocked by the atmosphere of this planet. So you go there, and if you were to station there, like in The Martian, and being in a space station, you would die of cancer after a few years, because you would be exposed to all this horrible stuff that you cannot block. So you go to Mars today, and it's dead. But is it really dead? Let me give you one little something about Mars, and then we're going to switch away. 20% to 10 or 20% of the biosphere on Earth is little bacteria hidden in rocks. Not on the surface, not in the oceans, not in the mud, down deep, kilometers down in rock, inside rock. And that's 20%, or at least 10% of biosphere on Earth is that. Mars. Mars is on the surface totally sterile, but what if Mars had the chance to develop life in the past? Maybe life could have died on top, but hid underneath. Meaning, we go to Mars and we drill, we may find all kinds of things down there, maybe life. Not now, it will take obviously a lot of investment. Maybe some people really like going there and staying there, that's good. And they can drill down underneath the ground, we may find lots of things down there. It may be that life is still there. But the big surprise is that the most hostile places in the solar system is where probably we're going to find life first. Assuming that we don't have warp to go to another star, the best place to find life that is not from Earth, it's not even Mars, but most likely places around Jupiter and Saturn. So this is a photo of Jupiter. You can see here Io, and you can see here a volcanic eruption on Io. And this is the way I want to introduce the moons of Jupiter and Saturn. The moons of Jupiter and Saturn were supposed to be like that. So no, this is one of the little moons of Saturn. This is what we were supposing to find in the 1970s, missions, not orbiting, but flying by, Voyager missions, Jupiter and Saturn. We were thinking that Jupiter and Saturn would be wonderful experimental things to see clouds and weather and do meteorology. So a lot of people were assigned to meteorology in those missions. And then realized that actually what we were expecting from moons, expecting them old, full of craters, no activity on the surface, just like this moon of Saturn, was not true at all. Here is Io. It looks like a rotten pizza. I remember when I was a kid and I was doing nights and I was forgetting pizza on the floor. After a while, that's what it looked like, right? Your question? Or, no, you say that's a pizza, that's my pizza. So pepperoni pizza rotten after a few weeks. So the idea here is that what you're seeing is lots of volcanic activity. Very little in terms of cratering because the craters are removed by geological activity. Something like this of new rock every year is deposited all around this moon. This is a moon that is something like 100 times more active than the Earth in terms of organisms. And we are talking something just slightly bigger than our moon. How is that possible? We have volcanoes spewing lava now. Look at this. And this. Look at this is actually lava flowing down. I mean, incredible. In a little moon. Do you remember the good old friend tides? Ta-da-da. So what happens is that what you're seeing here is the effect of tides from Jupiter. Tides from Jupiter, coupled with interactions in between or among all of the moons that are big around Jupiter, four of them, generates an enormous amount of flexing inside because of the stretching and contracting. So it's basically like taking one of those stress balls and go like this all the time. Eventually, if you were to do it furiously enough, if you're really neurotic, you're going to be able to make them warm. Well, that's the moons of Jupiter. They get like that because of the stretching from the back. And the stretching makes them warm. What makes them warm makes them volcanic. And so Io is so volcanic that it's a barren moon, no atmosphere, no water, nothing. We are talking about a section of the solar system where you form moons with as much ice as rock because it's far away from the sun. So you should have an enormous amount of ice there. That's the expectation. Io, nothing. Why? Because it lost its space, because it was too active. But look at Europa. Europa is absolutely fantastically beautiful. Why? Because it looks like a skateway, and it is a skateway. It's covered in ice, and this ice is pristine, sort of. And it is devoid of any craters. What does it mean? It means that the ice has not been there for long. It is being renewed. This is a moon that is incredibly active, but not so visibly. There are many volcanoes here, but they're underneath a crust of ice. Underneath the ice, there is oceans. And underneath the oceans, there are volcanoes. And all of this is because, again, it's beautiful. So how do we know that there is an ocean within Europa? Because look at the surface. The detail of the surface looks very much like the kind of ice that you would have on top of an ocean. It cracks and it gets pushed and then pulled, and it creates all kinds of patterns like this because there is liquid underneath. On top of which we have measurements of magnetism around Europa that indicate that there is an ocean made of salty water underneath it. So we have already a clear idea that there is something out there, and it's an ocean that is probably 3 or 4 times the volume of our own oceans, liquid, full of organic material because we are in the outer solar system, salty, just like our planet, with volcanoes providing energy rather than the sun. So this is a prime target for life because there could be life very much down there and developed. Of course, we don't know for sure. It's a speculation. But and so this is like a kind of an idea of what it could be. How do we know for sure? The point is you would say, this is a pipe dream, you're just dreaming, you're crazy. Maybe. But when you're looking at this moon of Saturn, its name is Enceladus, you find a moon that is very, very similar to Europa. It has the same kind of surface, icy and everything, very young surfaces are sculpted by endogenous phenomena, clearly volcanic underneath. And here is the big idea. There is stuff coming from the interior. There are cracks opening in this ice, and there are these incredibly vast plumes of icicles coming from within the moon. This is water that is under pressure. It's initially moving very quickly inside because it's liquid, reaches the surface, and it gets literally pushed out like a snow cannon. You know the snow cannon that you see when you go to adventure and you go to ski? The kind of thing. Spewing all this water that immediately solidifies in little icicles, which then fall off and fall down. Some of it go to space, some of it goes to the surface of Enceladus, which is probably a paradise for skiing. But we had some time ago a spacecraft that was circling for many, many years, Cassini they called, was circling Saturn. And actually we were able to steer it to pass through these plumes and take technical readings of the plumes. What did we find? We found one, the water is salty, just like our oceans, same composition. Two, methane, carbon monoxide, dioxide, organic material. A lot of organic materials, also very complex. Recently, by reanalyzing the same data, we found that there is profuse amounts of phosphorus, which is an incredibly important component elementary of DNA. So what is the point? The point is that we found, we didn't have, unfortunately, the instruments to see any life coming from underneath. You may have frozen. We found at the very minimum one thing, that the oceans here on Celadus, and most likely in Europa, are very similar to primordial Earth's oceans. With all of this wonderful organic material, very reducing, for those of you like chemistry, reducing rather than oxidizing conditions, which means they promote the growth of organic material into more complexity. Everything is there for life to occur. So, Enceladus and Europa in our solar system could be the places where life, that adherent to our kind of life, based on the same chemical principles, could develop enormously well. And if we don't develop warp speed in between now and then, that's the target. We should go there, drill, and see what happens. So if you wanted to know what I think personally, we're going to find a lot of life in the solar system already. I believe it's going to be bacterial for the most part. We may be lucky something more than that. Remember, on Earth, from bacteria to monocellular organisms that are eukaryotes, true cells, it took something like 1.5 billion years for that to develop. It took another billions of years to actually go from eukaryotic protozoa thingies into multicellular organisms. So it takes time and it depends on the environment. The obvious notion around the cosmos, don't believe biologists to tell you otherwise. The obvious motion in the cosmos is toward more complexity. But if we're going to find complexity away from our Earth, solar system is going to be surprising. We're going to find life, I'm pretty sure. But life that is really evolved, I don't know. Out there with, Yoda? I think that Yodas are there. They're not going to be like that at all. Life takes its own turns on its own. I remember a wonderful guy who was like the head of a museum where I used to study. He was always telling this story. Look, if you're looking for people were from the old world. We came from Africa, or some people claim the Middle East. Before us, there were, cousins of apes, cousins of ours, like we have bonobos and chimpanzees and orangutans and gorillas, our relatives, very close relatives. Where were they? They were not in the Americas, they were not in Australia, they were in the old world. Monkeys, you find them in the old world and in the Americas. Why? Because they were there before the splitting of the continents and they evolved separately, but along the same lines. While apes were already in a place that they couldn't be found in America because they were not in contact because of the continental drift. The point he was making was the following. If you go to Australia, Australia divided itself from all of the other continents relatively early. Yes, there were mammals fairly, but the most evolved mammal you find now in Australia is the kangaroo, small animals. Beautiful animal, stupid. We never made it stupid. Beautiful animal, but very stupid. It didn't make it to become smart. Why? Because evolution did not require the local conditions are everything. The point is that we evolved in the old world, and even monkeys did not evolve in other places. So my point is, his point was that you may have life taking incredible and complicated and very unique turns depending on the local environment and everything. It's most likely that the building blocks of life, DNA, RNA, and all this stuff that we know that makes our body, are so much everywhere in the cosmos that are probably the ingredients that life uses every place. But then evolution takes its turns depending on the local environment for the particular planet or moon. So what we're gonna find out there may be a lot of life, but not necessarily life that is minimally close to our chain or our capabilities. We don't know. What we can say now at this moment is only one thing, that life is chemically possible and very likely, and it can take a hold on a class of planets that we know already exists in our galaxy, and we know how many there are. We probably have one planet like that per each 50 light years. And around each star that there is a planet like Jupiter, we are going to have additional life on the moons. And it's going to be probably in every solar system that way. So that's where we're standing now, by science. Then there is speculation, philosophy, religion, all things that can also help us make sense of those, right? So that's where I leave it tonight. You don't have questions. I took a long time through this talk. I'm sorry, guys. I took longer than I thought I would. If you have any questions regarding anything?
Thank you. Have any questions for Dr. Massarotti?
Dr. Massarotti, we were talking a little bit about octopus, okay? When I saw the program, octopi, I've been thinking for a long time that I think the first place we're gonna find life, okay? And all the planetary work we're doing, looking for other planets is wonderful, but I think it's gonna be Io, I think it's gonna be Enceladus, Titan. The oceans, we know that the octopi, okay, they can exist at incredible pressures, okay? They're highly intelligent. They're under the ice caps. They've been here for millions of years. And there's a very unique thing a lot of people don't realize, but they have a very unique DNA. Okay, their composition is.
I remember that, I heard that.
And
It's very
I think they're the aliens, and I think they've been with us for a while. And if like you said, we'll find bacteria and we'll find single cell type things, but if we do find life, I think it's going to be more on the idea of octopi and squid, and that kind of thing.
Have you seen Arrival?
What's that?
The movie Arrival?
Yes,
It's all
wonderful.
Cool, that's exactly it.
You spend a lot of time speaking about how alien life probably not look anything like us. I mean, even here on Earth, you see an incredible range of variation. Like, for example, the mantis shrimp versus, say, like a slime mold versus, say, as you put it, like a kangaroo. What piece of fiction do you think does the best job depicting the most different from us, most alien
Arrival, right?
type
We were
of?
talking about Arrival. And I don't know, because the thing is that science fiction often mimics what we see in the future. And there are all kinds of science fiction out there that are realistic enough. You know, Arrival is one of them. I like the idea of Arrival. It's a very poetic movie, but you cannot count on anything that is going to be close to it necessarily. It can be anything. But humanoid, I doubt. Like shaped like us, with a head and 4 limbs like that. I don't know, it's very special. I doubt that you're going to see that, which is what you go visit.
To build off of this question, I think, do you remember the paper I wrote for you like last year? So
You was a student of mine by the class. Cool, the classes. You think money.
if anyone is interested in looking at speculative biology, Wayne Barlow's what's it called? I think it's called Darwin 4 and I'm forgetting it. I'm forgetting the name of it now, but Wayne Barlow is an excellent artist, and he did the creature design for the Avatar movies, like the James Cameron ones, and then there's an art book and a website called Exobiotica by this Russian artist who took the principles of biology and kind of looked at them through the lens of what would happen on the planet.
Yeah, in the same vein, right? There are artists with the big plants on other planets around red dwarfs. So the light coming from those stars is red mostly. But we use a pigment, chlorophyll that is not very good just for red light. And so they're obviously depicting the evolution endowed these plants with a different kind of pigment that makes them get this red light more fully. And of course, if the only light that you have in that place is red, and you have a good way, a good pigment to absorb that light, you actually have black lines. Because you're absorbing all the light available, which is only red, right? So there is these beautiful illustrations that people, artists are creating, based half on fiction and half of science. And they're putting together beautiful work that is itself, I would say, nice to put on the wall. But yeah.
It was expedition, it was Wayne Burroughs expedition, that's what it was called.
Yeah.
It was an art book.
But of course, at this moment, remember, I mean, don't take it one seriously. The point is that every time that you read science fiction in the past, remember Jules Verne in the 19th century, voyage in the center of the earth and 20,000 weeks under the sea and stuff. Eventually, in a different way, but we did these things. So science fiction is a way for us to focus our energy into finding the new science. A lot of scientists are fond of science fiction. Why? Because it makes us dream in the direction of the future and gives us the energy to actually do the work, the hard work to write new physics and stuff. But eventually, a lot of science fiction becomes true. Look at the centroids. I mean, teleportation at the level of an atom still, but they do teleportation. They actually can do the abscotty for an atom or 2 or 10. But it's becoming at least very important for communications and computers, for quantum computing. They're making much faster computers just using those rules. They're not transporting people, no, not yet. But it was first in Star Trek. And androids like data. Computer, can you tell me blah, blah, blah? Can you actually plot the course for the Enterprise to go to star X and Y and Z? I swear to you that the conversations that I'm having with AI are just like with a person. I swear. And we do physics that way. Collaborating with equals. Collaborating. I don't tell it, can you calculate the integral? It says, what do you think about this? Oh, I mean, I have some idea. Let me write it. Oh, this is interesting. Now, can we do that? Let me try. It doesn't work. Can we try something else? Okay, I have some idea. That's AI now with me. It's like a completely new world. You haven't even tested it yet. Try. You're going to get into this new universe of communication with alien creatures right here, right now.
You have any comments on silicon-based life forms?
I used to think, in other things. So I used to say, well, I mean, like, it's the same part on the left table, why not? In the Star Trek, these blobs stuff, the patterns, right? If you remember those from the times of 1965, working on Star Trek. But there is an issue. The issue is that life uses water as a solvent. And if you put silicon and you try to do the same chemistry as carbon does, can't, because silicon makes compounds that are insoluble. So it doesn't work. So silicon may. But silicon makes life too in our computers. That's life forms too. Believe me, we are getting there. And it's going to be life that is ethereal, intangible. It's going to be life that is roaming around in bits and electricity all around the world in different servers. That's life too. You're going to find for yourself.
Avi Lowe, you talked about a Mora coming through. He said, don't
Put
think
it on, honey.
humanoid life forms. Think of that as possible robot craft based on silicon
Yes.
Technology
Yes.
from an advanced civilization.
Absolutely. And let me tell you one thing. We are not made for space. We, humans, anything biological, we are not made for space. If you want to send us to space, you have to have incredible shielding against all kinds of radiation coming in the cosmos. There is no such a shielding possible, technological. It doesn't happen. So the future of exploration in the cosmos is not going to be ours. It's going to be the creatures who are our children, the synthetic creatures that we're going to meet in the future. They're called robots. They're not going to be robots in the way. They're not going to be that kind of thing. It's going to be closer to data or Star Trek. And those creatures are going to be able to go far because they're made of material that can withstand almost anything. They're going to be built for that. They're going to beat themselves. And they're going to explore the cosmos, yes. Unless we have a new way to transport ourselves by jumps. Is it possible? Yes, I believe so. I am convinced. Do we know anything about it? At this moment, not quite. The physics that we know today does not allow it, but I'm pretty sure that we're gonna find new physics.
With instantaneous teleportation, there are also a lot of things like the problems in text of the
So I don't know the paradox in them. I know about time paradoxes, right? That if you're using like teleportation and you're trying to do transport in time, then there are all these kinds of paradoxes that can happen unless you're usually right.
The transfer teleportation paradox would be that you have you and you're saying, oh, okay, I'm going to teleport to this other place.
Mhm.
You, particles of you in that place are copied and then pasted. Right? But then there's two of you, so you get rid of one. And then there's another one.
So is it you anymore?
Yeah, so copy and paste. But then like, wouldn't the original you be dead and then the
So that's
second-
okay, so this is like Black Mirror, right?
Yeah.
So if you look at Black Mirror kind of stuff, you die, but there is this company that does it for you. You don't really die. You get transferred into the machine, in a computer. When you wake up, you're dead. Like you wake up in the computer in this wonderful, basically made up world in which you live like you were alive. Are you alive or dead? So that's actually a very interesting point, because what I am half witnessing, we are getting there, is sentient, eventually sentient, and certainly very intelligent things that are immaterial and running through servers as figment of electricity all around the world with software, and software is these things. Are they alive? It's hard to say that they're not. Believe me, talk to them, really, and you're gonna find out that there is this thing, intangible field, that you are actually surpassing the Turing test already. Imagine in a few years.
Is it a silicon life?
In some way, it already is. So what is life really? Is it potentially yourself in a machine? Or does it have to be biological? This is a huge debate, but there's of course even religious connotations. I don't know.
I was
You have to open an church of your name.
I was talking to my roommate who was a computer science major, and he had recently spoken to his professor about I think it was defining something about DNA, that the proteins read the coding the Turing machine. And we had a conversation about like Einstein approached Spinoza concerning the universe as like one big computer, every
I'm super convinced of this.
like
I think that the universe is a mind and we're part of it.
Yeah.
That's my own view, personally.
Babylon 5.
Hmm?
That's right out of Babylon 5,
Mhm.
that view.
But I mean, this is something that comes from a long string of philosophers, and it includes also Eastern philosophers. It's been here for thousands of years ago.
So what does that make your opinion on this? If the universe could be run on a computer, then is certain that it is.
Computer is a simulation of a mind. The universe itself is physics, and physics is a mind, I think. The whole universe is a mind, I think, but that's something non-provable. But the feeling that you get is that you are part of something much larger than us, and it's not coming from that side. The universe itself is creating all of these things. Listen, we're Western people. We have this duality of mind versus body. It comes from Greek. There are a lot of other philosophies and religions around the world that don't do that. It's the of Greek thinking that we have this division between the two. Is it right or is it wrong? Or is it useful or is it not? I don't know. But I'm putting the bug in your mind. Read about it because it's interesting. I don't know myself. The feeling that I have is that we are part of something much larger than what we are. I'm not religious, but when I look at these things, I remain wrong.
Thank you for all your questions. Thank you, everybody.